So section 4.3 talked about the log function. And the log function gets introduced as the inverse of the exponential function. So let's look at some graphs of the log function. We'll start with the log base 2 of x. Now, if you're curious on Desmos where you can find log of just any old base, then go to the keypad, functions, and scroll down to calculus, and you'll see log base A. That's the one you want. You don't want just log, you want log base A. That'll allow you to put in whatever you need in terms of a particular base. When we're looking at base 2, this function is the inverse of 2 to the x. Remember that they're symmetric around the line y equals x. They're inverses of each other. Now let me get rid of these two graphs, and let's start playing with this one in a couple ways. In one of the homework problems, you're asked to kind of identify, well, which graph goes with which? And your choices are these below. Let's see if we can't predict the changes made on these things first. So if I multiply this by a negative, what's that going to do to the graph?
Reflect across the x-axis.
Reflect across the x-axis. Excellent. Glad you're getting good at these things. Let's see what else we can do. We can put this negative in the parentheses. That's going to reflect
Y-axis.
around the y-axis. Good. And then we can do both. So let's shut this one off. So the additional change is I need to reflect this green graph around the x-axis, so it would look like that. Yay!
Would you get the same thing if you reflected across the x first and then the y?
Yeah, it doesn't matter what order you do that. You know, if I did one and then the other, or the other and then the first, I'd still get the same graph. Yeah. So as far as the answer on this sheet is concerned, let's see. We'll start out with that one. This one right here, number 3, would be log base 2 of x. And then if you flip that upside down, that's going to look like this one. So that's going to be 1. If you reflect this around the y-axis, that's going to be this one. So that's going to be a 2. And this one has to be 4. And that looks pretty good. You reflected this down across the x-axis, so that's your 4 right there. Nice. So kind of a friendly one to get started with. One thing I want to note for you here when we're looking at this graph is that the graph comes close to but doesn't quite touch the y-axis. That's this one down here. That means its domain is 0 to infinity. You can't take the log of 0. If you do, for instance, your calculator is going to bark at you. Start trying to take the log of 0, and it says, oh, error, domain. It's telling you, quite literally, that you can't do that. All right. Now, along the lines of logarithms is kind of understanding really what the logarithm is telling you. And I know I've done some of these examples, but I want to go over this a little bit more in depth because I'm going to give you a general rule that I usually don't give out till section 4.4, but I'm going to give it to you now because you'll need it in the homework. When you're doing the log of something, you're really saying, well, what power of the base gives me this? So 3 to the 4th power gives me 81. But how about this one? What power of 7 gives me 7? Well, this is really 7 to the 1st power, but what power of 7 gives me 7? Well, that's just the 1st power, all 1. And coming down here, log base 8 of 1 over 8, I'm going to rewrite this as 8 to the negative 1st power. But that's not going to change the answer. What power of 8 gives me 8 to the negative 1st power? Maybe negative 1. How about this one? What power of 6 gives me 1 over 36? Keep in mind that 36 is 6 squared. But if I want that squared term to be in the denominator, I'll write that as 6 to what power? Not 6 to the 2nd power, but 6 to the negative 2nd power. What power of 6 gives you 6 to the negative second power? Well, I'm hoping that you're starting to see a little pattern here, right? When these things match, what's your answer? The answer is just what's in the exponent, right? How about this one? How can you rewrite the square root of 7 with exponents? That'd be 7 to what power?
Let's just scroll down a little bit.
I'm sorry.
You're good.
Thank you. So up here, this would be 7 to the 1/2 power. Remember, 1/2 power is just like taking a square root. Anyone want to hazard a guess as to what log base 7 of 7 to the 1/2 is?
1/2.
1/2. And 100 is really 10 squared. Writing it like that so that the base here and the base here match gives me a 2. So what you're seeing in all of these is that when the base here and the base here match, your answer is just the exponent. And that's an important property. You see it for all of these here. So to kind of summarize that property, I've written it right here. And I wrote it kind of in a bunch of different colors. I hope it's not confusing. What I want to draw your attention to is this. When this and this match, they cancel, and I get what's in the exponent. The reason for that is because these are inverse functions of each other. For instance, if I took the cube root of a cubed, I get back to a, because these functions cancel each other out. So the same thing's happening here. You've got a function, which is your log, and the inverse, which is the exponential. They cancel each other out and give me an x. Now the property that you need in this section is right here. B to the log base b of x is x. It's kind of the flip side version of this. So instead of f of g of x, you're getting g of f of x. But these are inverses, and you get x. So let me zoom out a little bit, keep this one in the picture. How about 5 to the log base 5 of 26? What would that give me? 26. Excellent. How about 4 to the log base 4 of 7? 7. And the one that looks a little tricky is this one. It doesn't fall in that pattern. In fact, Kyle asked me this one earlier. You've got e to the ln of 20. Well, I don't have bases that look like each other. Until you remember that ln is really log base e. And if you write it like this, then this one gets a little easier. That's your 20. Beautiful. So keep that in mind. You're going to need that for a few of the homework problems. But let's move on down to example D here. Kind of a nice quick one. One of the things I recommend that you understand is how to go back and forth between exponential functions and logarithmic functions. And the way to do that is to start out with the base. That power equals this. So can anyone tell me what the equivalent expression is using exponents? How would I write this without logs but with exponents? What to what power equals what?
X to the 1/2 equals 8.
X to the 1/2 equals 8. Excellent. No pun. So I still have to solve for x. Now the trick in solving for x is to raise both sides to the reciprocal of this exponent, the reciprocal power. So that'd be a 2. These exponents multiply when you remove the parentheses. So 2 times 1/2 is just 1. X to the first power equals 64. Beautiful. Done. That's the base here. That works for this one. Thoughts on that one? Doing okay here?
Wait, can you go back for just a second?
Going back for just a second.
Could you say that last part really quick for x 1/2? How do you solve that again?
Sure.
How did you get to, or why?
Well, I want to raise both sides to some power that's eventually going to put a 1 here. And I realize that if I multiply 1/2 by its reciprocal of 1/2 is 2, then I'll get 1. 1/2 times 2 gives me 1. But the thing is, the reciprocal is telling me what power I want to raise both sides to. I think there's another part of this problem in your homework where you'll have, like log base x of 4 equals 1/5, for instance. And that would be x to the 1/5 power equals 4. And so if I want to get rid of this exponent, I need to raise both sides to the reciprocal power. So what's the reciprocal power of 1/5?
5.
5. And you see what's happening here? 5 times 1/5, that gives me x to the first power. And I'm pretty sure that 4 to the 5th power is 1,024. But Dylan will check me on that one. All right.
All right, thank you.
Yeah. Thank you. Okay. Let's finish it up with a couple more regarding logarithms. One question that is likely to appear on a future exam would be to graph this and show me the points that you use. Now, what I would suggest is that you take this function and rewrite it. 5, log base 5 of y equals x. Can anyone tell me what that would look like using exponents? What would be the equivalent equation?
5 to the y power equals x.
5 to the y power equals x. The base to this power equals this. Now, what we can do, since we don't have y solved for, we've got x solved for, is we can flip things around. I'll plug in values for y and get values for x. So I'll plug in these values for y and get values for x. So for instance, 5 squared is 25. 5 to the first power is 5. 5 to the 0, 5 to the -1, and 5 to the -2. So those would be your points. So nice. If I want you to graph those and show me the points that you use, those would be the ones I would strongly recommend. What does that look like, say, on Desmos? Oh, I'm glad you asked. Here you go. Let's see, I need to zoom in a little bit. There's that last one. So kind of tough to draw this one here. It's getting really, really close to the y-axis, but it never touches it. In fact, let's actually put it in the graph. There's our graph. Comes close to, but doesn't touch that. And that's because the domain of this starts at 0, but it doesn't include 0. So the domain is 0 to infinity, and the range is -infinity to infinity, or all reals, like that. Understanding that graph, and in particular its domain, makes it a little easier to understand this graph. This graph is just shifted compared to this graph. How is it shifted? X minus 4 is going to shift it which way? Right, left, up or down? William's saying to the right, and he's correct. It's shifting to the right by 4. Now, our previous example right there had a vertical asymptote at x equals 0. So let's put that in here. Vertical asymptote at x equals 0. That vertical asymptote is going to get shifted in our new graph. So the vertical asymptote for this one, let's see, where do I want to draw it? Let's see. Vertical asymptote for this one is going to be x equals 4. But let's see what else gets shifted. One of the questions I got on this kind of stuff earlier was, Well, what's the domain of something like this? And for the domain of something like this, probably one of the easiest ways to solve this is to say, you know what, this expression, the argument, has to be greater than 0, which means x is greater than 4. And that's your domain. You could write it in interval notation as 4 to infinity. Parenthesis around the 4. The range is still the same, negative infinity to infinity. But the nice thing is I didn't even have to look at the graph to see what this was. It's just solve it with the algebra. Probably the fastest way to do it. You can take a look at the graph and make sure that it lines up with your expectations. Make sure that the domain is going to be 4 to infinity. Let's shut this graph off. Well, let me turn this graph on and then shut this graph off. You can see that this graph has been shifted 4 units to the right. The point that was at 1, 0 is not 5, 0. It's been shifted. And if you really want to drive the point home, you can draw on the line x equal 4. That's your vertical line. That's your new asymptote. So it's not really a part of the graph. It just kind of reflects a feature of the graph. So, nice. Comments or thoughts on any of those? Cool. Let me let you get working on that stuff.
Can you do one more domain problem, or?
One more domain problem? Sure. One last domain problem. Let me do one kind of similar to Kyle's from earlier. Find the domain of y equals log base 9 of 3x minus 12. So, okay. The thing that you have to worry about is you want this to be positive. So I would start there. I would start with 3x minus 12 is greater than 0. 3x is greater than positive 12. X is greater than 4 again. Beautiful. I didn't mean to use the same vertical asymptote as the last one, but the idea is still the same. If I were to graph this, I should see my graph have a vertical asymptote right at 4, just like the previous one. Let's double check that our graph matches our expectations. So I'm just going to modify that to a 9, and then this in here to 3x minus 12, and perfect. That's exactly what I expected. Starts at 4 and slowly grows. Its domain is 4 to infinity. Its range is all real numbers. It eventually gets as high or as low as you want. Although this is a very, very slow growing function, I'd probably have to go out to Main Street or Campbell Road to graph things, you know, even as modestly high as 6, something like that. Because it just gets crazy how big these numbers get before you move up the y-axis. Cool. All right. Thank you. Did that help, Dylan?
Yeah, that makes sense. Thank you.
Good.